Good morning. Good morning, you guys. I'm happy to be here. I wasn't sure if I'd be able to do it this week, but I got a little bit done today. So I have to go to my job, but it's okay, not so bad. I'm doing a little bit later today. I don't know, on the mornings when I have to go in earlier, I'm not sure if I can do this, but it's okay not to have it every day. But I was thinking this week, Tuesday and Thursday, but I might do it every day if I have time. If I have to make a picture that it's like I understand it better, and then I have the picture. Okay, so today I was just going to talk about what's a fine filter, because in the definition of super compact, it's a normal fine measure on p kappa theta. So okay, and then also I know that my niece, my niece Genevieve sometimes watches this, so I was going to add something at the end that's a little bit about the bigger picture. What are we doing here and what are we talking about? Okay, so the first slide here, I just want to talk about what's a fine filter. So this comes up a lot. So I believe that fine filters, this is from YEC, the definition that I'm using, are specifically for filters on p kappa theta or p kappa A. So p kappa A means subsets of A of size kappa. So in that picture there, you can those are all supposed to be like the same size. So A's bigger, has a bigger cardinality than kappa, and so this picture is showing all the so what p kappa A looks like. It's like all these. Usually we'd be just like on a line, but like a cardinal theta or something. But just to get the idea, so we have this. We have the set A, the bigger set A, that's the bigger set, and then these are all subsets of A of size kappa, so they're all the same size. Okay, next slide. So then we have this kind of pretty picture, it looks like a flower. So we consider all the x hats. So x hat is the set of y in p kappa A such that x is a subset of y. So it's like you have this set A, and then it's all the things that contain it. So sort of these bigger sets that contain it. Okay, and so I'm thinking about how with like a non-principal ultrafilter, we can't have the filter can't look like this itself, but our filter is just going to eat. They're just going to they want to put things like this in their basket. They want to include things like this. Okay, so on the next slide. So we have this so U is a fine measure on p kappa A if U is a kappa complete ultrafilter on p kappa A such that x bar is in U for all x in p kappa A. So it's all these little flowers that this guy wants to eat. So I think he's going to eat it, or maybe he's going to put it in his basket. But to him, these are big, and ultrafilters they take and they want the things that are big, and so they eat all these flowers type things. Okay, so yeah, it kind of reminds me of not a principal ultrafilter in any way, but sort of, it's like he's eating principal ultrafilters or something. Okay, so he eats all these. So that fine measure. Okay, so I feel like that definition, when I just look at the definition, the text, it's a little confusing. But this is sort of now I imagine that these sorts of things, these flower-like things, are all in the measure. Okay. And then tomorrow I was gonna do also normal filters today, but I didn't have time. So also my Notability is it's really frustrating because it's not working, because it's I can't draw, and I don't, maybe something wrong with my pen, hopefully, but that really gets in my way if I can't draw these things. Okay, so that's it. I feel like maybe it's not that enlightening. I don't know, but at least we can see what it looks like. There's something to draw for me. It's something comes to my mind when I think of fine now, it's eating these flowers. Okay, so the next slide, this is just planned for what I'm going to say. I've been thinking about it a little bit, but there's this picture. This is so this is that's all the set theory the definition that I was going to do today. So this picture we have here. Then so the next slide. So this picture we have here is okay. I didn't really plan what I was going to say, but so we imagine this room that I'm on this slide here is supposed to be all of math. So you think of all of math, and we sort of found this house as a community, humanity sort of found this house along the way. So there's axioms of math, and you can think of it as like the foundation of this house. It's like the things that we need in order to do all the math. So like some of the axioms that we have in math are like there's infinity exists. If you have two elements, there's a set that contains the two elements. So it's like all these, like the empty set exists. So it's all these kind of basic things about math, and these axioms sort of build this house of math. So you can do all the math that you want to do, you can do it in this house. I want to point out that we found this house. This isn't like, it's not like mathematicians were like, what are the axioms? Let's come up with the axioms and then we can do math. It's like people have been doing math for a long time. And at some point there was some pressure and someone was like, what are the axioms of math? What are the things about math that are true? They're basic, but we can't prove them because it's a basic fact. Like infinity exists. I can't prove that that's true, but but we believe it's true. So it's sort of a backwards history, a little bit. I mean, it reminds me of art. My niece loves art. So I called my mom the other day and I was like, oh, hey, Mom, what's going on? And she's like, and my niece is in the background. She's like, oh, I saw your videos. Like, oh, what video? And she's like, oh, the one you just posted. So like, I think she's watching. So I think of it sort of like the history of art. So in art, they didn't just start saying, okay, what are the colors? How do they go together? This is like color theory. They were just like, let's make a beautiful painting. Let's make a beautiful thing. And then later on, much later, they were like, oh, why is this color next to this color? Why do I feel a certain way when I look at this color? They sort of dissect. It's like math too. We already had the axioms. They already existed. This house already existed. We've been doing math in it for a while. But at some point, the set theorists, that's what I study, is set theory. The set theorists were like, wait, what is all this stuff? What is the actual math building itself? Where does all the math contained? Okay. And then once you figure out, okay, so it's sort of like they have all of math contained in this place, and we're gonna do math, sort of math on math. So now some people look at this house, and again, this house was given to us. We did not build this house. Okay, so you can do all kinds of things now. So some set theorists, so what I like to do is sort of look at the things that are independent. So like in the room, that person's saying, should we paint the wall red? Okay, no, we don't have to paint the wall red. That's like an independent statement. It's like these large cardinals that I talk about. It's like, that's not integral to the structure of the math house, but we can talk about them. We can say, okay, I want to talk about this really big infinity. So all the things I'm talking about, these large cardinals, these are all really big infinities. And they are not integral to the structure of the house, but you can have them. You can say, okay, I want to have an inaccessible cardinal, so I want to put an inaccessible cardinal in my house. And I think of it like, oh, the person in the drawing says, should we paint the house red? Because it's like, whether the wall is red or not isn't going to affect the structure. You can paint the wall red if you want. This is sort of like, let's say you think the real numbers are the first uncountable cardinal. So you say, I think the real numbers are red. So you have a red real numbers. Or some people might say, I think the real numbers are blue. So there's sort of these like flexibilities in math. It's very interesting. It's at the very top. After you do all the math that you have to do, all that math, then you can look at it like this. Okay, so there's certain things you can do. So I'd say painting the wall red would be that's a metaphor for saying like, the real numbers are certain cardinality, or like, oh, I have an inaccessible cardinal that comes and lives at the house. Let's see. Okay, also some people look at this math house and they say, what happens if they're wild and crazy. They might say, what happens if I take down this wall? What if we don't have this wall? What if we don't have a roof? What kind of math can we do in this house? Okay, so the people that take away the axioms. There's some people that say, you know what? I think there's more. I think there's a house that already has the walls painted, that knows what color the walls are, and I'm gonna keep looking for that house. You can do that. So you can do all kinds of things. So this is sort of at the end of the road, the math. Okay, and just one more thing. My niece is actually very good at math. She's 8 years old, and when she was younger, she had her own theorem. It was called the equals plus. And so she'd say 4 equals plus, and you're supposed to know what that means, and it means add 1. So she would, because she got sick of just keeping, if you're trying to do count 20 people coming to a party and one more person comes, she got sick of recounting. So she invented a theorem. Okay, I don't know if Genevieve remembers that. She was like 5 years old. Anyway, Genevieve's super good at math. Genevieve, if you're listening, thanks for listening to the show. And set theory is very interesting. It's sort of like at the end of math, or math about math, or there's a lot of flexibility too. You can paint the walls red or pink or whatever. Okay, anyway, thanks for hanging out, you guys. I'll see you soon. Bye.